Okay, we're going to go over half-life, which is essentially a decay rate. So there's a formula here, and this can also be used as a double time, sometimes you refer to it like that, or a growth rate. And the formula pretty much states that the amount of something left over is equal to the amount we started with, times the base being 1, which means 100% of the material we start with, plus the rate of change. So rate of change with half-life is actually a subtraction of 50%, right? In other words, the word is a half. So in our case, if we're talking about half-life, R would actually be equal to negative 0.5. So that's what we plug in for R, okay? Our T is time passed. And our H would be considered the time for half-life. So they usually call it half-life, but what would be a better way to describe this? Maybe as the time for the actual percentage, the full percentage to occur. So what we mean by that is in order for it to occur, let's say the half-life of something is 1 day, right? Well, if 2 days have passed, then we have 2 divided by 1, so in other words, we're going through the process twice, which makes sense because we go half and then we go half again. Okay, so this kind of stands for how long that procedure takes for. That's what our H is. So they've given us a question where we start with 100% of some object. What do they call it in this one? Plutonium. They give it a name. So plutonium, some substance here. Not plutonium. No. Polonium. 218. And we start with 100% of it, and then after 1 minute's time, we're left with 80%. So let's kind of write those factors in. So 1 minute has passed, okay, and after a minute there is 80% left, okay. So what that means is our 80%, let's highlight this there, perfect. Our 80% is essentially how much there is. We start with 100% of the object, okay? Let's get a pen here. That's going to be our A naught, which is 100%. We'll highlight those. So our A naught is going to be the 100% that we started with. Our rate of change, our R, is our 50%, right? Because it's a decay rate. Oh, that wasn't a good color to use. Let's use a different one. Maybe yellow is good. There you go. Okay, so we're going to plug that in. And time passed has been a minute. So 1 minute has passed, so that's essentially what our T value is going to be. So we're left with the actual half-life itself. We don't know. So let's plug all these values in. There's a lot of colors there. So we're left with 80%. So as a decimal, that is 0.8 is equal to 100%, which is a value of 1. Okay. 1 plus negative 0.5, which is 0.5, or in other words, a half. And that's usually how they write half-life formulas, is a base of a half, because we're constantly halving, okay? But that's how they derive it. 1 minute has passed. Oops, sorry. So time passed is a minute. What we're looking for is how long the half-life actually takes. How long does this how long does it take for our half-life to occur? So we're solving for H. So we need to isolate this question here. Now, luckily, this is times 1, so that's not going to really do anything for us. But we want to bring down this, we want to bring down our exponent here, and we're going to need to look into log functions. So in order to bring this exponent down, we're going to find the log of both sides. So log base 10 of 0.8. You could also represent this as 80 and 100. The ratios will both work. So log of 0.8. And log, this 1 essentially we know cancels out. And the 1 over h will become the coefficient when we make it a log. So this becomes 1 over h times log of a half, and a half is essentially 0.5. Okay? So what we're going to do here is we're going to bring our values to the other side. When we bring our log 0.5 to the other side, it becomes division. So this would become divided by. So we're left with log base 10.8 of log base 10 divided by 0.5. That makes sense so far? Is equal to 1 over h. And we have a situation where we refer to a lot in elementary school where we can kind of cross multiply, but essentially the idea here is if we flip this and flip this, we end up with the exact same ratio. And that can be shown with by looking at really simple fraction ideas. Think of it like 2 over 4 is equal to 1 over 2. We know that's true. If we invert both sides, does it still stay true? Well, then it says 4 over 2 is equal to 2 over 1, and we know that's true. 4 over 2 is 2, and 2 over 1 is still 2. So we can do that to essentially not have to go through that long process. So we now have h over 1, which I don't need to write in, is log 0.5 divided by log 0.8. Okay, and then this comes a simple calculation with our calculator. So 0.5 log base 10 divided by 0.8 log base 10 is equal to 3.106. We'll round it, we'll say approximately 3.1. Okay, so in other words here, because we're in the same unit as we put into t, our h, or half-life, takes about, looks like 3.1 minutes in this case. Okay, so if we plugged in 3.1 above, we would have discovered that we'd be at 50% when we go through this entire process here.